Hello, this is the next video in a playlist that I'm calling Probability Measure, and here we're going to look at the distribution function in space. And let's jump right in. So the interval, the way we're going to define interval in space is we have a n tuple, called A, and B is an n tuple, and they both live in Rn space. And we define this right semi-closed interval as all the x's that live in Rn, such that each component, so xi, the ith component, is greater than ai and less than or equal to bi. This is for all I, so every component has to satisfy that. Now, a distribution function on Rn is this: let x, let this n tuple live in Rn space, and we define f as this. So f is a function of the x1 through xn, and it equals, now it's some set measure, right, because it has to be a value, and it's all w in Rn space such that the first component of w is less than or equal to x1, and then each component's the same. So this vector only has the nth component that is less than or equal to xn, and that's for every component. Now, whenever we talk about distribution functions and measures in space, it's easiest to bring in the difference operators, delta. It looks like a triangle, but it's a capital delta, which stands for difference. So if we have a function that goes from Rn space to the reals, then we're going to define this difference operator as this. So remember this, the input is in variables, right? Outputs are real. But the delta of bi ai, this only affects the ith component of this function, and it's defined like this. So we take this function and we put in bi for the ith component, right? And then we subtract, and then we put in ai in the ith component. And that's it. This is the difference operator of f. Now here's an example. So if we have delta of b1a1, delta of b2a2 of this function, f of x1, x2, you do the first difference operator first. So then you put in, b2 here, right? And then you subtract, and then you put in a2. So we have this, but we still have this delta here. So then we put in b1 for here, and then subtract off, and then we put in a1 here, and that's what we get here. Now, graphically, what that represents, this is a distribution function, so it represents everything, below here. And then we subtract off b1, a2, which means we subtract off this piece here, and then minus f of a1, b1. So that means we subtract off this piece, right here. But notice that we've subtracted this region twice, so we add it back. So we add one of these, and then what's left is this, right? And this is a right semi-closed interval in 2 space. It's a cube, but that's the equivalent of a right semi-closed interval in 1 space. Now, we're going to call this a measure. So it's the measure mu of the right semi-closed interval a to b. Now, where a and b live in R2 space, right? And we're going to set that equal to the double difference, or the difference operator twice on this function. That represents this value. And in a couple videos, we're going to call that the Lebesgue-Stieltjes measure. But for now, we're not calling it that. So a few notes: when n is equal to 1, so a and b are part of the reals, then this function, that mu of ab, which is just delta of ba of f of x, is f of b minus f of a, which this is the Lebesgue-Stieltjes measure. So in 1 space, or in the reals, then this difference operator produces the Lebesgue-Stieltjes measure. Now, let's assume that f is a function from in space to r. A is less than or equal to b, so these are vectors in space. And we call f of AB. So remember, this is a right semiclosed interval. That's this region here. Up in 2 space, it's this. But in space, we can't really graph it. We set that equal to the in difference operators. For each component, we do the difference operator on this function. Okay, that's what this equals. Now, to be right continuous in space means we take vectors, x1, greater than or equal to x2, greater than or equal to x3, and those converge to x. Now remember that each component has to satisfy this inequality all the way down until they all converge, so every component converges to x. And notice there that it's convergent from the right, in quotes. So that means that f of xn, which are these vectors, and as n goes to infinity, it actually equals f of x. That's what we mean by right continuous. Now, increasing in space is a little bit tricky. One would argue we need to bring in partial derivatives and stuff like that. But for distribution functions in Rn space, that we define it like this, that this f of the right semiclosed interval is greater than or equal to 0. Remember, this is the defined like this. It's the difference operator on each component. If this is greater than or equal to 0, whenever a is less than or equal to b, and this for all a and b, then we're going to call it increasing. It's an increasing function. Now, f is a distribution function if f is increasing and right continuous. Then that's what we call a distribution function. Now, one last theorem, and then we'll call it quits for this video. Let I be this right semiclosed interval in space, right? So this A and B are 2 points in space. But let's pick 2 points C and D that are between A and B that hold this relationship. Now, as a reminder, A, B, C, and D are all vectors in space. But this relationship, it creates a grid, right? And it's 3 to the n disjoint intervals, and we call each of those I sub j, right? So we've just made this I into a grid of 3 to n little disjoint intervals. Then f of I, remember this is an interval, so that f is really that difference operator, the difference operator on all n components. That's equal to just the sum of f of I for each of those disjoint intervals. And the f of CD, this smaller interval, is less than or equal to this larger interval. And so this is analogous to in one space, or the real numbers line. Now, to prove this, it's sort of tedious and quite laborious, and so I'm only going to give you an idea of how to prove it, and we'll just call it quits. So I call this an outline illustration of the proof. And we're going to do it in 2 space. And so we have the 4 points, A and B, and then we have C and D in the middle. And of course these are in 2 space, so it's a tuple. And then this can be thought of as this grid. So you take the first component and you plot them here. Then you take the second component and plot them on the second, we're in R2 space. And then these create a grid, right? Now, here we said that it creates 3 to the n, but we're doing with n equal 2, so 3 to the 2 is 9. 1, 2, 3, 9 disjoint intervals of the interval A to B, right? Now, we're going to focus on just these 2 intervals, right? And we're going to think of this first rectangle as one piece or one interval for now. But let's, and based upon what we've done, that is this difference operator, right? So B2, C2, so B2, C2, that's this, and then B1, D1. So that's this. So we've created this little interval using the difference operators. Now, we learned on the previous page, when we're in 2 space, it's actually this function here, right? So it's B1, 2, so it's, you know, everything below, subtract off this piece and then subtract off this piece, but we've subtracted this off twice, so we add it back, and then we're left with just this rectangle. Okay. But let's bring these down. So that's this. B1, C2 is this piece, this is that, this is this. And then we add 0 to it. So we add and subtract the same quantity, add and subtract the same quantity to this right here. But then if we focus on this piece here and then this piece here separately, this piece here is actually this disjoint the interval. It's the 1, right? So D1, B1, yeah, so D1, B1, and then oh, I have the numbers. So this should be B1, D1, and B2, D2. So maybe I should fix that live. Dang it. So, and this is a 1. So D1, B1, and then this is D2, B2. Okay, we're going to have the same problem here. This is the first component, this is the second component. And I'm going to have to, in the interest of time of the video, I'm going to have to let you correct the subscripts. But anyway, this piece here ends up being this interval, and then this piece here is this double interval for 2 with the correct indices. There should be 1s here and then 2s here. But so this the whole rectangle is this measure, and then the first rectangle with the 1 is this measure, and then the second integral is this. So that little rectangle up here, the measure of it is actually the sum of the individual measures, and that's what we have just shown here. Now, we didn't prove this because we didn't do it in generality. We just did it for 2 space for just 2 little things. But you can then see that if this interval is a subset of this interval, then the measure of this is less than or equal to the measure of this, right? So if we have the measure of 1, that's always less than the measure of both, you know, assuming that mu is that as a distribution function. It's right continuous and increasing. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.